has started. Not that people who are talking would hear me say that the recording has started, but whatever. So,
Are they hurt?
on Friday, let's start off class day with reviewing some of the things we did on Friday and talk about how they apply to your lab. On Friday, we started talking about energy conversions, okay? Converting one form of energy into another form of energy. And we said that one important concept that we have to make sure that we understand is this concept of conservation of energy. That when we look at the big picture, the total amount of energy that exists in a closed system has to be the same at the end of the situation as it was at the beginning of the situation. Now, when we talk about energy, we're talking about the total amount of energy, right? All of those different forms of energy that we talked about, not just mechanical energy, okay? However, in certain situations, we can see a conservation of mechanical energy. And we said that was the case if we have what we call a conservative force acting on that object. So, two examples of conservative forces, gravity and elastic forces. Okay? And what makes those conservative forces special? How are they different from other forces, at least from an energy standpoint? It's up on the board right now. So they don't change the actual amount of energy, but they will change one form of energy into something else. Okay? All right, so let's apply to our lab. Okay? So our big pendulum over here, right? First, I do this to the pendulum. Okay? Did I do work on the pendulum? Yeah. Okay, yes. A couple of reasons. First, did I apply a force to it? Did it move because of my force? That's work, all right? Second, does the object have more energy now than it did before? Yes. Specifically, what kind of energy? Potential gravitational, right? So this object is going to start with potential gravitational. It doesn't have any kinetic yet because it's not moving. But if I let it go, what's going to start happening to it?
The kinetic goes higher.
Okay. Gravity acts on it, pulls it downward, right? As it's moving from here to here, right? It's going faster, but as it's going faster, it's getting lower. So potential is decreasing, potential gravitational is decreasing, kinetic is increasing. Okay? Rush, as it applies to our lab. In theory, or theoretically, how much kinetic energy should it have down here at the bottom? The same amount as the potential gravitational that it started with. Does that make sense? Okay? So, Durant, that should give you one of the columns, or at least the one, I think there was one column in the calculation table. Technically, it's more along these lines, Durant, okay? When we have only conservative forces, so if there's only gravity and or a spring force, we say that mechanical energy is conserved. Because remember, conservative forces don't change the amount of mechanical energy, they just turn one form into something else. Like in that pendulum, gravity is turning potential gravitational into kinetic. Okay? So, when mechanical energy is conserved, it starts off looking like this. NEI equals MEF. Mechanical energy initial equals mechanical energy final. That's what conservation means, right? However, what do we know about mechanical energy? What is mechanical energy? It's actually a combination of some things, right? So we can actually spread that out or break it down a little bit more to look like this. Okay? On the left-hand side, right? Let's see if this will actually work. I'll actually write on it. Over here, the initial mechanical energy is equal to the kinetic energy at the beginning plus the gravitational potential energy at the beginning plus the elastic potential energy at the beginning. in the case of our pendulum, Niraj, is that pendulum moving at the very, very beginning of its motion? Right after I let it go, is it moving? Right after the instant after I let it go, it stopped. Right at the beginning, if I'm just holding it up here, Niraj, what is it? Is it moving? It's not. So does it have any kinetic energy? No. So that's 0. Does it have gravitational potential energy? Yes. So it has some of that.
This is for the theoretical.
Yep. Is anything being stretched or compressed, Niraj? No. So that's going to be a big 0 as well. So in the initial mechanical energy side, what's the only kind of mechanical energy that it has at the beginning? Gravitational potential. Okay. At the end, right? Let's see if this works. Okay. At the end, which would be the bottom of its motion, not all the way back on the other side, because remember we put the photo gauge right at the bottom of the motion, right? What is it doing down there when it passes through the photo gauge? Definitely moving. So does it have kinetic energy? Actually, yes, very much so. Okay, but does it have gravitational potential anymore?
No.
Not really, because of the fact that we subtracted that height off the table, blah, 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 right? So it doesn't have any gravitational potential. Does it have any elastic potential? Didn't stretch or compress anything. So that's still 0, right? So now we can take this formula. So as far as writing out the calculation, right? Start it with this. Start it with MEI equals MEF. Then we can apply that to our specific situation by saying, what kind of energy does it have at the beginning? PEGI equals KEF. You've already calculated PEGI, right? So then you can just say that means the number I calculated for PEGI must be the same as what KEF would be. Okay? Now, remember, this is all theoretical, dependent on the condition that what's the only force acting on the pendulum as it goes from here to there? Gravity. Was that actually the case? No. Okay? Did we get into that on Friday? With the friction and what friction does and stuff like that? Okay.
Out of the theoretical kinetic energy, is it the same as initial PEG? Like number-wise?
No, that's good. Okay? That's okay. Alright, so if they're really offhand, but let's go here. Let's talk about that. Okay. So here, good question. Is it bad that your measured kinetic energy and your theoretical kinetic energy aren't the same? No, that's good. Because to get the theoretical kinetic energy, we're assuming what about that pendulum? That what's the only thing acting on it? Gravity. Was that the case? No. That leads us into non-conservative force. Did we do non-conservative force on Friday? Okay. So, non-conservative. Okay. Non-conservative forces make it so that mechanical energy is not conserved. Okay. This equation that goes along with it, it looks kind of funny, but I think we talked about this on Friday, yes? Okay. That the W stands for work, delta ME stands for change in mechanical energy. So the amount of work that you do is equal to the change in the energy. Okay? There are only 2 conservative forces, which means how many non-conservative forces are there? Lots. Pretty much everything else. Okay? The first thing I do with the pendulum, when I take my hand and I raise it like this, right? Is my hand a non-conservative force? Does it change the mechanical energy of that object? Yeah, it gave it what kind of energy? Gravitational potential. Okay? So, if we take a look then at that case, okay, now, once I let it go, my hand isn't acting on it anymore. What is acting on it? Gravity, true. But is gravity the only thing, though? No. There's air resistance, and then what else is there? Friction. Okay? So let's talk about friction. Okay. Mostly friction up here, Miriam, there's like some friction with the string as it like kind of moves across this. But a lot of it's air resistance. But air resistance and friction are pretty much the same thing, okay? Just to a different degree. Okay? But, so, friction. First, what do you know about friction? What did we learn about friction in the last chapter? Which way does it act on stuff? Opposite direction. If it's going in the opposite direction of a movement, is it going to do work on something? Yes. Specifically, what kind of work? Negative work, right? Did we get this on Friday or no? Okay. So, friction is a non-conservative force, and it does negative work. If we're doing negative work on something, what happens to its energy? How about what happens to it? It decreases the energy. Okay? Now, a lot of times, if it slows something down, that means it's decreasing what kind of energy? Kinetic energy, okay? Which happens. Okay? But, more importantly, though, one of the very first things that we wrote down on Friday was conservation of energy. Conservation of total energy. So while it's decreasing the amount of mechanical energy this object has, what must be happening somewhere else? Or to some other kind of energy? Some other kind of energy has to be increasing. Generally, what happens to things when friction acts on them? Yes, they slow down, but what generally happens to them? They get hotter. Right? That was kind of weird the way I said it, but they get hotter. Right? Rub your hand on your pants 3 or 4 times. What starts happening to your hand? Starts getting warm. Right? I just said a couple of times. Right? Relax. Easy. While mechanical energy isn't conserved, the total energy has to be conserved. So what friction does is it takes, friction will take mechanical energy and turn it into non-mechanical energy, usually heat. Okay? Other non-conservative forces will take non-mechanical energy and turn it into mechanical energy. For example, my hand. Right? My hand gave that pendulum mechanical energy, specific gravitational potential. Where did that come from? What did I have to do in order to... Yeah, but how do I work? Yes, okay. What do I have to do in order to have the quote-unquote energy to lift this pendulum up?
Equal and greater.
I gotta eat food, right? So we said that food was a kind of chemical energy, right? So my hand is turning chemical energy into gravitational potential or mechanical, right? Whereas friction turns mechanical into heat, right? The thing that makes conservative forces different from non-conservative forces, it turns mechanical into mechanical, right? Gravity turns gravitational potential into what? Kinetic. Whereas friction turns gravitational potential into heat of some kind, or something like that. Does that make sense? Okay. But that's non-mechanical. But gravity, that's what makes friction a non-conservative force. Okay? Raj, theoretically, how much kinetic energy should that pendulum have when it gets to the bottom? As the potential that it started with. But if you look at your measured kinetic energy values, what should you be seeing about them in reference to your theoretical kinetic energy values? They should be lower. Okay? The measured kinetic energy values should be lower than your theoretical kinetic energy values. If that's not the case, okay, now we talk about that in terms of sources of error and stuff like that, okay? But, did we do the demonstration? Did we do the, oh yeah, you did it, right? Yeah, the base.
This is kind of, like, could your hand also make it static? Like, what if you held the pendulum and moved it?
If you pushed it, yes. Okay. But now, see, I'm getting back to forms of energy. Now, once again, you're turning chemical energy into mechanical energy, whereas it's a non-conservative force, but it's not the only non-conservative.
Okay.
Yeah. And then, go ahead. Hold on a second. That's where we're going today here. All right. Are we good with this? Review from Friday? Okay. Did we get everything that we needed to get now?
Wait, on the conclusion question,
Yep.
for the last one, like comparing air resistance and friction.
Okay. Okay. So, Caroline, what's the resistive force that the pendulum encounters? Pretty much air resistance, okay? But the ball rolling down the ramp is going to encounter air resistance, but it's also friction because it's rolling down that ramp, right?
Yeah.
So, in theory, what should we see about the differences for the ball versus the differences for the pendulum? The differences for the ball should be higher. Are you going to see that? I don't know. Maybe not. Okay. No, the ball should be higher because the pendulum basically just encounters air resistance, whereas the ball encounters air resistance and friction from the ramp. Okay.
Isn't that kind of like if the ramp was a non-friction thing, the ball go faster?
Maybe. That would depend on like the size of the object and what it's made out of, because then we get into like what air resistance is affecting it and stuff like that. Thank you. Glad we got that on recording. So. All right. Are we good? All right. Here we go. Good question. Let's transition us into the next part of today. So, what we want to do this week is we want to start talking about non-mechanical forms of energy, specifically one type of non-mechanical energy, and that's thermal energy. Okay? So, Nick, warning. Okay? Today, I'm going to introduce you guys to a couple of terms. And a lot of these terms sound similar, at least the way that you understand them at this point in time. I caution you, please make sure that you keep track of which term means what, because if I'm asking you about a specific term in a short answer question or something like that, you need to know what it means so you can answer that question properly. Okay? So, with that being said, let's start here. Okay? First, I hope this is reviewed by now. What's energy? The ability to do stuff, or the ability to change stuff, right? We said that energy is kind of a change agent, making things different, okay? Or the ability to move or change matter. Okay. What you actually write in that space, I really don't care as long as you understand that energy is this ability to change things, to make them different than they were before, okay? We're going to talk specifically about thermal energy over the next couple of days. And we said that thermal energy, Miriam, you kind of mentioned it, thermal energy deals with a motion, right? But it's a motion of what? Atoms, or we could talk about not just necessarily atoms. What if we're talking about it's atoms if the thing we're talking about is an element, but it could also be what? How about the pieces of a compound we would call a molecule. So, more generally, the energy associated with the movement of microscopic particles. And when we talk about those microscopic particles, we'd be talking about either atoms or molecules, depending on, what kind of a substance we're dealing with. Whether it's an element or whether it's a compound. But the important thing here is it is a movement. So, it is a kinetic energy, but now we're talking about kinetic energy on a small scale versus like a whole object. Okay. So the movement of microscopic particles, those microscopic particles specifically being atoms and molecules. Atoms and or molecules. Okay. All right, good there? Okay. First term that I'm going to introduce to you that you need to make sure you understand. Heat. Okay? By definition, heat is a transfer of thermal energy from one object to another because of a temperature difference. What does that sound a lot like? Sounds a lot like work, right? Because what are we doing with work? Transferring energy, right? So what's going to happen in the case of heat? There's going to be a what? A transfer of energy or a change in thermal energy. Okay. Which way does thermal energy flow? From hot to cold, right? Energy will flow from hot temperatures to cold temperatures. And specifically, heat being how much energy flows from a high temperature to a cold temperature. All right, we good there? So heat flows spontaneously from hot objects with high temps to objects with cold temps. If we're going to use temperature to define heat, we probably should define temperature. So we've talked about temperature already. What do we say the temperature sort of tells us about an object? Or the stuff that makes up an object? I would say that's a different term. The movement, right? So temperature tells us the average kinetic energy of the particles in an object. So temperature measures the average kinetic energy of particles in an object. Now, a couple of things. First, does that mean that every particle in either of these two beakers here is moving at exactly the same speed? Not necessarily, right? Because it's an average kinetic energy. Second, because it's kinetic energy, what does that mean the temperature depends on? Movement, specifically, what about the movement? The speed, right? So the next thing on your outline, right, it says right above the picture, it says this depends on the what? Speed of particles, right? However, does kinetic energy only depend on speed? No, right? What else does it depend on? It depends on the mass as well. So if we're talking about two substances at the same temperature, does that necessarily mean their particles are moving at the same speed? No, it also depends on what? How big those particles are, right? Water, relatively small, right? Those particles move pretty quickly. However, something like cooking oil or something like that that has a bigger structure, those particles may not move quite as quickly because it tells you about the kinetic energy. Okay? So
This is related to the speed and mass.
Technically, it's related to the speed, but it also depends on the mass as well. Okay? So if we're talking about the same substance, right? If we're talking about water going from 50 degrees to 100 degrees, that's going to be a speed thing because the mass doesn't change. But if you're comparing different substances, now there's a mass factor. Okay? So, question next to the picture on your outline. Okay? There are these two beakers here. And one beaker has the ice underneath it, one beaker has the fire underneath it. And what do you see about the little whoosh lines that are following those particles around? One's bigger, one's smaller, right? Why are these bigger?
Because it's heating up.
Right, it's hotter, right? Cold temperatures, less motion. Warm temperatures, more motion. The less motion indicated by the shorter lines, the more motion indicated by the longer lines. Good.
What if the ones that were just heated up went to the ice, but they had like sugar in it? Or like, what was...
Hold on for that just a second. I think what we're going to talk about next will answer your question. All right, we got that written down, summarized somehow, some way. Okay, let's talk about changing temperatures. All right. In order to understand this idea of heat and energy flowing from high temps to low temps, we're going to step out of the realm of small particles and go back to big particles. Okay? Let's talk about these billiard balls here. Okay? 9, it's the one with the yellow stripe on it. Okay? Is traveling towards your right, towards the 2, which is the blue one. The 2 is not moving. The 9 is. They run into each other. What happens to the 2 because of the 9 running into it? It bounces off, right? But if we talk about its speed, right? How fast was 2 going before 9 ran into it? 0. How fast is it going now? Maybe not necessarily the same, but it's going faster than it was before, right? What about 9, though? What has to happen to 9? It has to slow down because of what idea? Conservation of energy, right? Before 9 runs into 2, 9 has all the energy because it's moving and 2's not. But if it gives some of its energy away to 2 to make it go faster, what has to happen to 9? It has to slow down. If we now apply that to temperature thing, what is 9 representing? High temperatures, right? It's moving quickly. But when high temperature things come into contact with low temperature things, what happens to the low temperature things? They move faster. They get hotter. But the high temperature things must then necessarily do what? They have to slow down and cool down. So, objects with heat flow spontaneously from high temps to low temps, right? Using this picture, explain why. The one big idea that sort of governs that is what? Conservation of energy, right? That if things moving quickly run into things that are moving slowly, the slow things speed up, the fast things slow down. So did you write something along these lines? Doesn't have to be word for word, just as long as you get the gist. How long does this go on? Until they're equal, right? Because Grace, if they're equal, right? If one runs into something else, it's like they have the same temperature, right? Now it's not exactly the same. It's not exactly the same as the billiard balls, but that's just sort of an idea, right? That heat will flow spontaneously. Energy will flow spontaneously from hot things to cold things until they're the same temperature. Okay? If you leave a bowl of hot soup on the counter for a long time, it loses energy to the air because it's hotter than the air. That will continue until what? Until it's the same temperature. You don't come back after 3 hours and your soup is now like cold, right? It's cold, but it's not freezer cold, right? Because it'll stop transferring energy as soon as what's true about the soup. It's the same temperature. It's room temperature because now the temperature is the same. Okay. Good. Absolutely. I mean, if you think you're like on a cold day, you can get your hands warmer just by holding them over your cup of tea, right? Yeah, if it was a really closed system. Now we get into the idea of closed system from like last week. We're actually going to make use of that tomorrow when we talk about calorimetry. We talk about how much energy is actually moving around. Okay? Yeah, go ahead.
Space is really cold.
Yep.
Right? It's like Earth. It's like temperatures.
Because we have gravity that kind of holds those particles close to us, and so those particles can't necessarily get away from from the Earth because the gravity's holding on to them.
So that's why like higher altitudes.
And actually, too, we have like less movement there because there's less particles as well. Okay, Chris, go ahead.
So does that mean like the Earth's average temperature is always the same?
Theoretically, yeah. Although, depending on who you ask, it may be increasing or decreasing depending on not necessarily a transfer of energy, but in what we're doing here. But we're still, in order for Earth's average temperature to stay the same, all the energy we get from the sun would somehow have to be given off to the surroundings somehow. Okay. What's happening is that based on factors that we believe we're doing here, that's causing us to hold on to more of that energy as opposed to radiating it back out into space. So that's causing the average kinetic energy of the particles here on Earth to increase, and that's why the average temperature is increasing. Right. Global warming in a nutshell. Carly, go ahead.
Why does heat rise as heat rises?
That gets us into a little bit more. Actually, hold on just a second. That's sort of the end of this.
Okay.
We might have to wait until tomorrow for that.
Okay.
That's okay. So. All right. Let's talk about another term: thermal energy. Okay. Thermal energy is the total damage that we can do because of this motion of these atoms or molecules. The total amount of motion of the particles that make up an object. And when we talk about particles, we're talking about basically two things, right? Could be atoms, could be molecules, depending on what substance we deal with. But the total damage that can be done depends on a couple of things. What is it going to depend on?
Temperature.
It's going to definitely depend on temperature, right? It's going to depend on how fast those particles are going. But is that the only thing it's going to depend on? What else is going to influence it? Well, kinetic energy is more of a temperature thing, right? The mass is also going to influence how much damage can be done, right?
It could be like exposure time.
Exposure time kind of more has to do with how much stuff is there, so that would be more of a mass kind of thing, okay? Because, Nick, if we're going to have a long exposure time, that means there's going to be a lot of stuff there, okay? Although, state of matter and temperature are closely related to one another, but when we talk about the total damage done, we're not just talking about one factor, we're talking about a lot of factors. Okay? So, let's talk about,
So why is thermal energy total damage?
so let's talk about this 4th of July sparklers here. Okay? Say again? Yeah. Because he's foolish. He's foolish.
I stepped on with my bare foot.
So, Nick, not to make light of your situation, but have you stepped on a sparkler before? Okay.
Back when crossed
So-
the pool.
So, do the sparks that come off of the sparkler have a high temperature? Yes. Because what are those particles doing? They're moving very quickly. So that's the first question there, right? Do the sparks have a high temperature or a low temperature? They have a high temperature. Because why? Because the particles, the molecules, the atoms that make up those sparks are moving very quickly. Are they hot? Yeah. Right? That's what we define hot as, right? Yes. Can they hurt you?
Yes.
Will they transfer energy from their sparks to your skin? Yes. So that means they have, because that's saying that they have more energy than your skin does because it's flowing from hot to cold. Okay? Now, big picture though, okay? Nick, not to make light of you stepping on a sparkler, but in the grand scheme of things, stepping on a sparkler hurt, but it didn't do a lot of damage.
No.
Not really, right? I'm not making light of your injury, but you're not permanently maimed or anything, right?
No.
Okay. So,
Couple minutes of pain.
a couple minutes of pain, right? So, okay, now that's when we get into it, right? The sparks have a high temperature, but they don't have a lot of thermal energy. Why not? they're moving very quickly, but how many particles are in a spark? Not a whole lot, right? So, yeah, they hurt because they transfer that energy from them into your hot to cold, but because their mass is so small, do they do a whole lot of damage in the big picture? No. So they have a high temperature, but a low thermal energy. Okay?
So
Oh, go ahead.
it's no because there's not a lot of particles in one of the sparks.
Right. That we said that thermal energy depends on a couple of things. It depends on the actual temperature, how fast the particles are moving, but also it depends on the mass, or how much of it there is.
Grab the hot fireplace thing.
Okay, now
That
that
actually hurt my hand.
Now that probably did a lot more damage, right? So if you grab the hot poker from the fire, right? But you probably should have taken this class earlier, I'm thinking. But anyway, Nick, we'll get into that tomorrow, okay? All right, are we good with those definitions to begin with? Okay. For tonight, there is a short little reading assignment and a couple questions from the book. Also, take-home quiz right up here. Yeah, take-home quiz. On the red shirt right here. Grab one.